I
Okay, this
appreciate
is
you.
the November 17th Eclipse volunteer moving with guest star Brian Mendez. I guess we'll start with some general announcements first.
Yeah. Laura, do you want to talk about EclipseCon?
Yeah, let me tell you a little bit about EclipseCon. I have a slide that Hannah made actually, which I really like. Um, okay, what? Oh, I always do that. Okay, can you see it? Great. So, we are combining an Eclipse mega movie project review with a workshop to reflect on the two magnificent solar eclipses and several lunar eclipses that have occurred in the last since 2017, basically. And if you want to think about others that you've been part of, great. So that's going to be held here at Sonoma State University, and it will be on from March 24th to March 26th. It'll be like a conference. There'll be a sliding scale registration fee. You got to get yourself here. We'll have a block of rooms people can sign up for. You can talk if you want, or you can just come and listen. And then you can go, if you like wineries, you can go visit some wineries. If you like the ocean, you can go hang out on the beach. If you like the redwoods, you can go hiking in the redwoods. If you want to go get a tour by the folks who do eclipses at the Exploratorium, they're going to put together one. So if on your way up here you want to stop in San Francisco and do that first, you're welcome to. So we'll have some of the folks from the AAS, the American Astronomical Society's Eclipse Task Force are going to be joining us and being part of that. And when we did a survey, about 40 people said they would like to travel here, actually, and another 20 said they'd like to join via webinar. So we'll have both options. So we'll put up a registration page in a bit, pretty soon. I talked to Troy about that recently. So that's in our next sprint. And that's it. Any questions?
Don't put the emergency brake on so hard and don't put the one on.
How close is it to Quarter Madeira?
Oh, that's a good question. I don't,
I have some friends in Quarter Madeira that I might be able to crash with.
to stay with. Um, but I don't know actually.
About 45 minutes.
Oh, that's not so bad.
No?
Great. Thank you, Hannah. You figured
Mhm.
that out fast. 45 minutes. That's a good amount. Yeah, come stay with friends and family. Okay, great. All right, I'm passing it over, or anything that Dora or Hannah want to say. I guess my other update is that as we've been saying this already, but our data, our level 0 data is online, so you can get to your data. And oh, when does the registration start? Yeah, Dora, we have that on our timeline when the registration will be up. Do you remember? It was like November. I don't remember.
I cannot remember
I know.
either.
I think it's right before. I think it's soon. I think it's like next week.
We're definitely trying to get it out before winter break, right? Because everyone's making their spring break plans already for next year. So we want to be on people's radars.
Exactly.
And as soon as it's up, I'll be sure to send a listserv blast like I do for these meetings.
Exactly.
I have a question about that data,
Yeah.
which I sent in to Hannah. Um, some of the data is, at least in my files, has been duplicated. And I'm not sure whether it was duplicated because something messed up or whether it was duplicated because the load failed in the middle and I had to start it over.
Interesting. That's very good to know, Spencer. This is what I wanted to hear. Um, okay,
Could
great.
you send that email to me one more time, please, Spencer?
If he has the time, he says.
Sure.
If I can find it, I will.
I believe in you.
Okay. Yeah, and you might be able to do a from Spencer too. I don't know, Hannah, to find it.
I did that and I couldn't find anything.
Oh, I see. Maybe it went to a different Hannah. Um, okay. Yeah, and we'll have the level 2 data. That's also really good to know too, Spencer, because it could affect the way our HDRs are being made. I hope not, because we've been spending a lot of time on those HDRs. So, we'll.
I think that I mentioned it in the
Oh,
uh
in the Discord.
in the my mind is not working real good with all of my
Yeah.
family problems going on.
Sure.
I think I did it in the survey.
Ah, okay. I'll go plumb that.
Oh, the Eclipse Megamovie survey. Uh-huh. Okay.
When we were talking about the data and if you saw anything wrong with it.
Yeah. Yep. Okay. Cool. Right. Okay, so if any of you also noticed that, let us know. The FITS files are coming out. So uh we're excited about that as well. That also has been taking an outrageous amount of time. But making FITS files is no small feat from scratch. First have to come up with your FITS headers. So we're almost there. It's very exciting. Okay, I think anything else before then I'm going to introduce Brian. Okay, let me introduce Brian to you all. Once upon a time, no, in a galaxy far, far away, Brian was a kid watching Star Wars. And really, that's what he wants to talk about. But I didn't get to meet him until well past that. But when he still loved Star Wars at UC Berkeley, he started the Space Sciences Laboratory. He and I started around the same time. And yes, and he is an astronomer. He got his astronomy PhD from UC Berkeley. And he studied, I can't even remember what you studied. Did you study galaxies? Yes. Okay. He studied galaxies, where they are, their distance.
Yeah.
Aha, look at that. I'm so proud of myself. He studied galaxies and how you can measure how far away they are, which is not an easy problem at all. It's getting easier with machine learning. I just read a paper. Did you see that, Brian? They're taking all the galaxies where they know where they are already, and they're training models on that, and then and then they just apply that to new galaxies. That learning. Anyways, that's pretty cool. So, but we grabbed him to do science education, or he grabbed us, or we all grabbed each other. I don't know. We were kind of working together. So we worked together for a long time at Berkeley, and he's still there. And he is a marvelous educator. I have had the pleasure of doing multiple teacher workshops with Brian, and it's really best if I can support him to do it, because he's just so good at the way he explains things, and you're going to get to experience that tonight. It's so exciting. And of course, he has a good grasp of astronomy and flats and all the things that you all had to learn about, calibration frames, and he's been in the background helping us this whole time. And he also was an Eclipse Megamovie photographer in this whole time as well. And then when we did the Eclipse Megamovie out of UC Berkeley, as I was talking to Spencer, he was helping us figure out kind of what we should tell you, what photographs we should tell you to take. Which since nobody had ever done something like this before, it wasn't obvious. So, and cameras were a certain way. Anyways, so Brian has this really big breadth of knowledge in science education and how to teach people about science and how to do outreach with different communities. And he's also just a really amazingly awesome person and kind and compassionate. So he's one of these smart, compassionate people. And I'm glad that I know him. And I'm glad you're going to get to hear all about Carruthers from Brian. All right, Brian, take it away.
All right. Thank you, Laura, for that very nice introduction. Um, Hi, everyone. Good evening. And I'm going to tell you about a spacecraft that just launched. Let's see, what's today? So we're just shy of 2 months from the launch in September. We launched September 24th, and it was very exciting. I don't actually have any slides about it. I should have added some slides about launch just for fun, but we can talk about that at the end if you'd like. But I'll tell you, what the mission's all about and what we're going to be studying. And hopefully I won't bore you. Hopefully I will intrigue you. So let me see if I can get this screen sharing thing to work first time. Do it. Hello. All right. Are we seeing the slide? Great. I'm going to move this elsewhere so I can see you and my screen. All right. So this is a picture of the spacecraft. I should say not a photograph, but a artist rendition of the spacecraft, and I'll show you more as we go on. But we're called the Carruthers Geocorona Observatory, and I'll explain who Carruthers was and what the geocorona is momentarily. And the cool thing about this mission is it's the first time that NASA's actually doing a mission to study Earth's exosphere. We haven't done that before. So it's always kind of fascinating because sometimes it feels like, oh, we know everything about Earth. But it turns out there's still parts of Earth that are just completely unexplored, like its outermost layer. So let me continue on then, and let's describe the exosphere. So in fact, the exosphere is the outermost layer of Earth's atmosphere. So in this animation here, you see the different layers of the Earth's atmosphere, which are defined mostly by changes in temperature and density. Pretty much everything you know about happens down in the troposphere, right? That's where we're at. That's where the weather's at. And, that's actually where 75% of the mass of Earth's atmosphere is at. It's all in the troposphere. And then the stratosphere you're probably familiar with. That's where you get those really high clouds. That's where airplanes fly. Then the mesosphere above that is kind of considered the top layer of the atmosphere. In fact, within the mesosphere, you've got 99% of all the mass of Earth's atmosphere is there. And we generally consider space to kind of start at the top of the mesosphere. So that's about 60 miles or 100 kilometers up is where within the mesosphere. And then beyond that, the thermosphere is where particles they go to really low density but very high temperatures. And at that place, you also have a mixture of particles that are neutral, which is the thermospheric particles, and then you have ionized particles, which form the ionosphere. So they kind of share the same space, but they're talked about and studied kind of separately because they behave separately because they're of their different neutrality and charged natures. And then above that is the exosphere. And the exosphere, so it starts at about 300 miles above Earth's surface, and then it just goes out into space, and we don't really know how far. So that's one of the things that this mission will help us figure out is like, what is the extent of the exosphere? The models we have suggest that it might extend halfway to the moon, which is pretty far, right? So that's exciting. So the exosphere is mostly neutral hydrogen gas. So there are some charged particles out there, but the majority of the particles that are in the exosphere are neutral hydrogens. So the simplest atom you can think of, right? You got one proton, one electron. And the density out there is really, really low, right? It's so low that these particles don't behave like the standard gas that you play around with in a laboratory or learned about in high school chemistry. It's what we call a collisionless gas because the particles never bounce, they never hit each other. They're so far apart, they're so widely spaced, the density's so low. So they're bound to Earth mostly by gravity. Well, entirely by gravity. Gravity is the thing that's holding them there. And they just kind of go around doing their business. The density's so low, there's no way we'd ever see them. And so the way that we can observe this part of the Earth's atmosphere is to use the fact that when sunlight strikes those hydrogen atoms, they the ultraviolet part of the sun spectrum will scatter off of those hydrogen atoms, and it'll bounce off in any old direction, and it creates this ultraviolet glow, which we call the geocorona, and that's kind of in analogy to the corona of the sun, right? The corona of the sun is the glow of the outer atmosphere of the sun. And so the geocorona then is the glow of the outer atmosphere of the Earth. For those who want the fine details, the actual there's a specific wavelength that hydrogen does most of this glow at, and it's called the Lyman alpha um, line, and it's the transition from the second excited state down to the ground state. So it's a pretty common transition. All right. Now, as I mentioned, this part of the Earth has been very poorly um, observed. In fact, since the space age began, there have been only 4 images, not just 4 like missions or anything, but 4 total pictures ever of the global exosphere ever taken. Part of the reason for that is because it's so big, you have to be far away to take a picture. And you also, in order to see it, have to have a sensitive ultraviolet camera. And a lot of spacecraft that go that far away from Earth don't have that type of camera. And then, it has to actually take a picture of the Earth. And so I'll tell you more about the Apollo 16. That was the first one that ever happened a little bit later here. But, Galileo was the spacecraft that went off to Jupiter. In order to get to Jupiter, it did these maneuvers around Earth, and it was using Earth's gravity to get a pickup of speed. And so on one of its passes, passes where it's fairly far away from Earth, it turned its ultraviolet camera in 1992 and took the image you see there. The SOHO spacecraft, which was launched in actually, it may have been launched before 97, but 97 is when they were doing calibration tests of the instruments and actually pointed some of the ultraviolet instruments in the direction of Earth, and they managed to recreate then some of the glow that's coming off of Earth's exosphere. And then, of course, this spacecraft, once it was finally commissioned, was staring at the sun and has been ever since. And then there was a spacecraft called Procyon. I actually don't remember what its prime mission was, but it was another one of those. It's doing an Earth flyby, and so, hey, let's put our cameras at Earth and see what we can get. And that's it. Those are the 4 pictures of Earth's exosphere. And in those pictures, what we can see is that it's really big. We can see that there's some interesting structure that's probably caused by interactions with solar wind. But since we have just one static picture, like with many, many years in between, we have no idea what's going on, dynamically with with the exosphere and how it behaves. So what we do know is that the part of Earth's atmosphere that we, are probably more familiar with is the part that's within the magnetosphere. So, right, the magnetosphere is generated in Earth's core. It's this magnetic field that surrounds it, and it traps charged particles within Earth's influence. And so the ionosphere, for example, is highly responsive to the magnetosphere, as are any particles from the solar wind that kind of leak in from the magnetotail or occasionally from the cusps. And so we have things like the radiation belts that are the Van Allen radiation belts that are controlled by the magnetic field of Earth. And that magnetic field acts like a shield, actually, against the incoming solar wind. The solar wind is mostly charged hydrogen, and when it encounters the Earth's magnetic field, it feels the Lorentz force, which pushes it off at right angles and protects us down here on the surface. So it's a pretty nice thing for us. But the exosphere is expected to extend way beyond the magnetosphere, right? If it goes halfway out to the moon, and this picture is kind of to scale, it gives you a sense that, yeah, the exosphere goes way beyond this. So the exosphere we know is interacting with the solar wind, but again, we don't have observations. We don't really know what that looks like. We're particularly interested in what the exosphere's role might be in geomagnetic storms. And these are the storms that happen whenever you get changes in the solar wind. Sometimes we very fast, especially very fast moving solar wind can generate these storms. So that's often caused by CMEs. There were some great ones that just happened, last week. We had like these, what was it? It was like a triple CME, and the last one was so powerful and fast it overtook the first two and slammed into Earth last, was that Monday? When I think it was Monday, right? And here in California, we didn't get to see all those amazing aurora that were happening everywhere else on Earth, but we had clouds. Such is the way of astronomy. But hopefully you saw some of the wonderful pictures of aurora that we're seeing. I think even in El Salvador, I think I saw someone showed a picture of aurora appearing in El Salvador as a result of the big geomagnetic storms that occurred last week. The aurora are kind of the pretty effects of the of geomagnetic storms. Some of the other things that are more concerning to us are the way it affects our technology, which, especially the technology that's in space, our satellites can be impacted fairly greatly from the radiation that comes during those types of storms. Communication with those satellites can be affected through the ionosphere. The ionosphere is strongly affected by those storms. Um, Very high altitude space aircraft have to be concerned about additional radiation, and often they divert planes away from the magnetic poles of the planet to cut down on the radiation that the crews are experiencing. You've probably heard about the induced electric fields that can happen on the surface of the planet, and those induced electric fields can mess with our power systems and even cause overloads. There have been large-scale power outages that resulted from these types of storms. So there's all kinds of effects. One of the ones that I find really interesting these days, and I actually encountered a farmer when I was at Kennedy Space Center, and we were doing some outreach at the visitor center there, and we were talking about space weather, and this farmer was there, and he was it was so amazing because he was wearing overalls and he had a big old hat, and it was just like, oh my God, you knew he was a farmer from far away. And he came over and he started talking. He says, "Yeah, yeah, we had a bunch of trouble last year." Because nowadays, especially in big, industrial farms, they're using automated tractors that use GPS to to either sow the fields or to spray them or to water them. And GPS gets messed up by scintillations that occur in the ionosphere due to these types of storms. And so the accuracy of the GPS goes way down during a storm. And that would cause these tractors to shut down, right? Because basically there's too big of an error, and so they trip kind of a fail safe, and the tractors just shut down, and the farmers lose a bunch of time, um, and therefore money whenever there's one of these big storms. And so that was something I knew about, but it was fun to actually talk to a real farmer about that, and he was telling me about his own personal experience with that. So it's one of these effects, these geomagnetic storms, that really impacts our modern technology, right? This is something that the sun has been doing for 5 billion years, but we've only cared about it in the last 50 years because we have technology now that's affected by it. Well, one of the things that we don't know about but have suspicions of is that the exosphere, we think, can actually help the Earth recover from these storms. And I don't know how much I'll give you a brief version of this, and then if you have questions, we can talk about it in more detail. But the neutral particles in the exosphere can actually interact with charged particles, and they can do this thing called charge exchange, where the electron from the neutral particle sees this proton flying by, and it decides to jump ship, right? It's like, I'm getting off this boat, and it runs over and it lands and turns that proton into a neutral hydrogen and goes off flying. So we've got these strong electrical currents that are running through Earth's magnetic field during geomagnetic storms. And as they encounter neutral particles in the exosphere, that charge exchange will happen, and it'll basically take the energy out of the current, because those current particles are suddenly turning neutral, and they're no longer feeling the magnetic field force, and they stop being a part of the overall flow of the current. So basically that's kind of how the we think a big source of energy loss for these storms is the exosphere. So this is something that we're really hoping that we'll be able to see in action as our mission starts to make its observations. One of the other things that we're hoping to understand about the exosphere is how what role it plays in the loss of water. So the hydrogen the net neutral hydrogen that's in the exosphere came from water mostly. And that's because water is made of two hydrogens and one oxygen. And when those get into the atmosphere, and form clouds and that kind of thing, there's several different ways in which those molecules can be split up. One of the fairly common ways is from ultraviolet light. Ultraviolet light comes in, breaks apart the molecule, and then the hydrogen atoms, they float up because they're fairly light, and the oxygen atoms will sink down. And over time, this is how a planet can lose water. And we know that process happened on Mars, and we've been studying that at Mars, and we know it happens on Earth as well. It's much, much slower at Earth, but it's something that, especially if we can compare the observations that we've been taking at Mars with observations that the Carothers mission will now take of Earth, we can build a larger picture of how planets atmospheres evolve over time and what role that plays in their loss of water over time. And that's especially of interest to exobiologists who are, they're taking in all these wonderful data that are now coming from these exoplanets that are being discovered all around our solar neighborhood and in the nearby galaxy. And we've been finding these rocky worlds that are in the habitable zones of their star. And, we wonder about are they really truly habitable? And one of the key aspects of habitability is, do you have liquid water on your surface? And so in order for us to be able to predict that for these exoplanets, we need to understand, well, what are the conditions that a planet needs to have in order to hold on to its water for a long time, like Earth has, right? Earth has held on to its water for billions of years, but Mars, lost it after just about 1 billion years, right? Mars used to have a lot of water, just like Earth did, but then it all went away. So that's one of the things that understanding our exosphere will help us in a broader sense understand about planets. All right. Well, let me tell you a little bit about Dr. Carruthers. He's the one on the right in this picture here. And his name is George Carruthers, and he invented a technique to see ultraviolet light and make images from it. So he built the very first ultraviolet telescope. And this was while he was working at the the Naval Observatory. And this technique was, pretty groundbreaking and exciting. And astronomers were like, oh, we have got to get this telescope out beyond Earth's atmosphere, because Earth's atmosphere absorbs a lot of ultraviolet light. So, pointing this camera at the sky from the surface of Earth, you're not going to see very much. So you got to get outside Earth's atmosphere. This was during the late 60s. And so one of the ideas was, oh, could we get this telescope on one of the Apollo missions and get it on the moon and have it take pictures? So our mission, in fact, still uses the same technique. And if you're curious at the end, I can tell you a little bit more about how that technique works. But we use, updated technology, but it's the same basic technique in order to convert ultraviolet light into visible light that then is captured by our cameras. So that was the trick, though, is they got this aboard the Apollo 16 mission. And here's a picture of Dr. Carruthers actually training some of the mission staff along with a couple of the astronauts. In fact, here's I'm blanking on his name, John Young, who was I think he was the commander of the mission, and he's the one who actually tooled around and put the telescope in place on the moon. And then here's the picture of I don't know if that's John Young or if he's the one taking the photograph. This is a fun picture. If you look at it carefully, you see this is one where the astronaut is jumping up, right, because they can jump so high on the moon, and he's doing the salute with the flag there. But right in the background where the arrow's pointing, that's where the Carruthers telescope was placed and took pictures. They took pictures around the sky and tried to see different things in ultraviolet. But of course, one of the sources they wanted to see was Earth, because they were hoping to see Earth's exosphere. When they didn't bring the telescope back, so the telescope is actually sitting on the moon there, still next to the LEM, and or at least the landing part of the LEM, and they just brought back the film canister that was there, and then the film was developed. And here on the right is so on the left, that's Dr. Carruthers holding the actual film canister after it had been returned from the moon. And then on the right is the image of the exosphere that it took. And the scientists who study the atmosphere and were thinking about trying to, what they were going to see, were really surprised because it was bigger than the field of view. The exosphere extended beyond the field of view, and they were like, wow, the moon is too close to see the whole exosphere. So, gosh, I guess we got to get even further away in order to see this thing.
Hey, Brian, there's a question about is the exosphere shape a ball or a bit changed like the magnetic field due to the solar wind or other aspects?
That's a great question, and we don't know. In the previous 4 images, you could see that there was some asymmetry, and it was, I think, along the Earth-Sun line. So we expect that there is probably some oblateness that's caused by pressure from the solar wind. But it's still more spherical than it's much more spherical than the magnetosphere, because the magnetosphere is feeling the magnetic force from the solar wind, which is causing it to distort. Whereas the only force that the exosphere would feel from the solar wind would be a gas pressure, which is very low at these extremely low densities.
And this charge exchanged kind of phenomena that you talked about.
Yeah, and the charge exchange phenomenon we think happens. Let me see if I can go back a few slides there. In fact, the IMAP mission that launched with us on the same rocket studies particles that come from that same process, but they study those charge exchange particles come from the outer edge of the solar system, from the heliopause. But the IBEX mission, which is the predecessor to IMAP, also was studying those same kind of particles, and it saw them form right in front of Earth. And so we think that those were exospheric particles that were interacting with the solar wind and creating a glow. So yeah, so there is some interaction there. So yeah, the bluish glow you see in this photo is kind of the general shape we think it has, but um, we have expectations. We think it probably changes with season as the Earth goes around the sun, but we don't know yet.
That's what you'll find out.
That's what
Does the
we'll be
charge
finding.
exchange, Tom's asking, does the charge exchange then make the exosphere take on a positive charge?
No, not overall, because it's a pretty uncommon thing to happen. So it's not
Because it's so
happening.
rare.
Yeah,
Yeah.
it's very, very rare. So overall, the exosphere maintains a neutral charge.
And then in the picture, Cos and Heather ask, in the picture with Carruthers and that awesome picture that got taken from the moon,
Oh,
what is there's like a half circle on the right.
oh yeah, that's internal reflection in the camera. So yeah, those of you who are photographers probably familiar with internal reflections that can happen. Yeah, so that's what you got there. You got internal reflection that's creating that artifact on the right hand side.
Thanks.
Yeah. Sorry, I forgot to put up the chat box. So thank you for monitoring the chat for me. All right, let's see. So here's some pretty pictures of the actual instrument. So the camera, there's well, it's kind of two cameras in one box, and one has a wide field of view, the other one has a narrow field of view. And they were built at UC Berkeley Space Sciences Lab. And the entire package is called the Corona Imager. And so you can see, I don't know if can you all see my cursor? Yeah, okay. So yeah, these are the doors that protect those. And those doors, they stayed open until, I can't remember now how many days into launch before they were opened up. But they protect basically all the optics from stuff that might be flying around during launch and that kind of thing. And then they pop open. And here's the instrument package being integrated onto the spacecraft bus, which was built at BAA Systems in Boulder. And they have tons of experience of building these things. They're it's kind of like it's not quite as the same as like the car. I'm blanking on the name. The car lines that they have, but they have so much experience making these things that it's always a great partnership when we are making those. No, I see Hannah has a question. Yes, Hannah.
Yeah. Do you want to talk maybe a little bit, Brian, about why the technician working on the equipment is dressed the way they are?
Oh, sure. Yeah, this is always a fun question because a lot of times, when people, I guess, in movies and things, when we see people in these types of suits, we often think, oh, they're protecting themselves from dangerous stuff in their environment, but it's actually the opposite here. We call these, I don't know why they're called bunny suits, but they're called bunny suits. And the purpose of them is actually to protect the instrumentation from the filthy humans who are always shedding their hairs and their skin cells and the breath off all that stuff is not good for the electronics. And so that is why the person here is wearing all that protective gear to keep the instrumentation and the electronics pristine. And then here's a view of the solar panel that BAA Systems also provided, and it provides us with a good amount of power. My zoom window here is blocking it, but I'm pretty sure the number was 194 watts. And it's going to basically, that panel stays staring at the sun throughout the mission because the eyes of the spacecraft are staring at Earth. So we sit with our back to the sun and stare at Earth. One of the couple of reasons I like to show this picture, so it's kind of shows you the complete integrated spacecraft. Um, and I like to, it gives you a sense of scale. You can see how big it is. When we were trying to write up, press releases for this, we were trying to figure out what's something in your daily life that's about this size. And the closest thing I could come up with was like a love seat sofa. But you can look in the picture and you can see, well, it's that big, right? There's a person, and there's the spacecraft. And one of the things that I've noticed is that, well, you know what? I'll save that for a moment. The other thing the point I really always like to make is that there are so many people who are involved in a mission like this. Sure, there are the scientists whose idea it was to do this in the first place, but even there's a bunch of people who are involved in that. But when you think of all of the technicians and engineers and all of the admin staff and all of those people who had to come together in order to put this together, I mean, it's a huge group of people who all have to do their work really, really carefully in order to pull something like this off. Here's our spacecraft at Florida before it was integrated onto the rocket. And so it was just hanging out there with the other two missions who were on the same rocket. It was kind of a really cool opportunity. We were on a SpaceX Falcon 2 or Falcon 9 rocket, and it's a pretty big rocket. And so they had space for three spacecraft. So it was a ride share. We're all going to the same place, so we all got together, hung out in this facility for a bit. And one of the things, so this is when I was giving presentations, especially over at the Cape Canaveral. I started to notice when the spacecraft all came together, I was like, wow, it's pretty cute when you think about it. Right? I don't know. I look at it, I'm like, wow, that's adorable. And then I was like, that reminds me of a particular robot that's in popular culture. And so maybe I'll have you all do it in the chat. I'll pull up the chat here. On the count of three, so you can start typing it now, and then on the count of three, I want you all to hit enter and tell me what robot does it remind you of? Okay. So ready? Everybody ready? One, two, three. All right, let's see what we got. Oh, there. Oh, one person actually said Robbie. Okay, yeah, and everybody else got Wally. Oh, and Hannah thought it also looks like ET. Yeah, I see that too, Hannah. But Wally kind of looked like ET, so yeah, when I was doing that, almost everybody said had had Wally for that. Does it have any jetpack or boosties? Yes, it's got, let's see, I don't know if you can see them really well in this picture, but it has several little rockets that are fixed on the bottom here. And yeah, those are used for station keeping and course correction. Laura doesn't see it. Oh. Well, these are the eyes, right, Laura? And here's his body.
I see. But where's its face? Like, where does it eat?
Very nice. Okay, let's see. And yeah, this is where we were all headed to, all three of us missions. We were headed to Lagrange point 1. So that's the place that's a gravitational balance point between the Earth and the Sun. As this diagram shows, there's actually five of them. And the first one and the most stable one is the one that's directly between Earth and the Sun. It's closer to the Earth. It's only about 1 million miles away from Earth, although 1 million miles is still pretty far away. And so this is a great vantage point to be able to observe the Earth from because you can hang out there. You don't have to expend very much fuel once you get there, and you can just stare in the direction of the Earth. Or in the case of SWIFO L1, which is one of the other spacecraft that was on the rocket with us, it's going to stare at the sun, just like SOHO. SOHO is also sitting out there at L1. And the IMAP mission, which I referenced before, is also going to go to L1. And I think the next, yeah, I've got a quick little video that just kind of shows as we launched 2 months ago, and then it'll take about 100 days for us to get out to that million miles away. And so just over 3 months before we get into orbit around L1, and then we're in a pretty big and large orbit. And actually, one of the cool things about this large orbit is it allows us to do tomography, right? So if you're familiar with like medical imaging where they put you in an MRI, for example, right? Or no, sorry, the CT scanner, right? It takes pictures from a whole bunch of different angles, and then so each one of those pictures is a 2D image, but because they're all from different angles, you can reconstruct them into 3D and get a 3D image of, the inside of your body, whatever part of you is being scanned. Likewise, because of the large orbit that Carruthers is going to have, um, we'll be able to kind of reconstruct what the 3D structure of the exosphere is over time. And because we're going to be staring at it for a couple of years, we're going to be able to see how it changes, how it evolves with season, with time, and even with, oh, sorry, I jumped the gun. I wanted to describe our communication flow. So we actually use NASA's Deep Space Network to talk to the spacecraft because it's so far away, you need to have a big radio antenna to talk to it. And then the communications are run through University of California Space Sciences Lab, which the arrow pointed at there in that picture, just up the hill from Memorial Stadium on Cal's campus. And then Berkeley takes the data that it downloads from the spacecraft and sends it over to University of Illinois, where the project's principal investigator works. Her name is Laura Waldrop. And I should mention at this point that one of the really cool connections in this mission, and one of the reasons why we decided to name it after Dr. Carruthers, is that this is University of Illinois' first NASA mission that they've ever led. And Dr. Carruthers was a three-time alum of University of Illinois. He got his undergrad, or I guess not three-time. Was it? Oh yeah, he got his master's there too. So he got his undergrad, his master's, and his PhD all at University of Illinois. So it just seemed like a really perfect synergy, right? The guy who invents the technology that our spacecraft is going to use, is also an alum of this university, and it's their first mission. So it seemed perfect. All right, here's a fun little movie that shows that moment when the eyes open up, and you can see there's two different sizes of the apertures, and that's for the two different cameras. The larger field of view that sees kind of the whole exosphere, and then the smaller field of view gets down in and sees kind of what's going on close to Earth. So we want to be able to get all of that. I see a comment that Spencer made that L1's getting pretty crowded. Yeah, I got a lot of questions about that when I was giving talks, and people asked, are they ever going to run into each other? And the thing that you got to remember that space is really big, and that these spacecraft are really small. So yeah, they're not going to run into each other. But yeah, L1 is a good place to be. So there's a decent amount of spacecraft hanging out there. Here's some simulated images of what we think the exosphere will look like. It's going to be monochromatic because it's all one single, it's just one color of ultraviolet, right? So the colors that we will put to the images that we eventually put out will be probably more about intensity and density. So you'll get a sense of that. And that's what's meant to be shown in these synthetic images here. We already have taken images of the of Earth's exosphere now as we're journeying to L1. So we're starting to do calibration and check out and that kind of stuff. We don't begin science operations until probably March. But we'll probably release to the public some first light images pretty soon. I'm supposed to talk with Laura this week and kind of coordinate on that. Yes, March is science. So right now it's all checking out. We still haven't gotten to L1 and got into our final orbit. So right now we're just trying to learn how this spacecraft behaves and how to make it operate at peak efficiency. Oh, so one of the points I was making earlier, or I was going to make earlier, was that within our 2 year mission, we not only will be able to see the Earth go through all its seasons and such, but we're also going to be experiencing the change from solar maximum, which we're just coming out of the peak now, toward solar minimum. So we'll be able to see how the exosphere may respond to the changes in the sun's input that comes from the changes in the solar cycle. So that's another kind of nice aspect of our timing for the mission. So 2 years is kind of the minimum mission. We expect that we can do all of the main science goals within those 2 years. But as with all NASA missions, we always have reserve, and so there's enough fuel on board to allow us to stay in orbit for 10 years. So hopefully we will manage to do that. It's always a cross your fingers kind of thing because you never know if the government will have money to be able to fund that for that amount of time. But we could continue to do this science for up to 10 years if the fates allow. And then when it's all said and done, when the mission is over, we'll actually leave L1 so that we're not in the way of all those other places. And we will send the spacecraft into a solar orbit where there it will just stay. It'll just orbit the sun for probably billions of years. And that's kind of a fun thing to think about. And I hadn't thought about that. It was Lara, the mission PI, who kind of thought about that. And she's like, that's really exciting for the students who've worked on this to think that, I'm going to be involved in building something that will last for billions of years, right? I mean, it's wild. And then when she mentioned that, I was like, oh, I always imagined that it would be a cool thing to do in the future, space tourism, right? You go out on your little space tour, space bus, and you go fly by some of the ancient artifacts from the early space age when humans were first going out, And so I imagine a trip to fly by Carruthers and, oh, look at the first spacecraft that ever viewed Earth's exosphere. So, all right, well, that, that is the story of Carruthers up to this moment. And very soon we should be like I said, March will be here before we know it, and we'll start to be doing science. So yeah, it'll be exciting to see what we start learning.
Where can we go for updates on this mission, Brian?
Oh, we can, well, NASA.gov will have updates, of course, and they're probably going to be the main place. We have a website that I run at UC Berkeley where we do educational activities, but we do have kind of a Carruthers section there as well. And so I'll probably update things as they happen there. But I would just say, if NASA.gov is probably your best um, first place to go for updates. Yeah.
Cool. And then how long after the science starts in March do you expect it'll take to publish something? I mean, not a paper, obviously, but to show something to the world.
Oh, I expect we'll probably, I'm like I said, I think probably within a couple of weeks here, we'll probably put out our first light images. And so I
Ooh.
expect that we'll start putting out images, pretty soon after science begins. Though I'd like to, set expectations. You saw the synthetic images. They're not going to be, it's not going to be like James Webb Space Telescope type
Sure,
images.
sure.
It's going to be a fuzzy round blob. But
Like
you know,
our solar corona pictures.
yeah, right, right. Yeah, but it's what that's what that fuzzy blob tells you is the exciting part, Let's see. Spencer asks Apollo 16. Yeah, it was Apollo 16 in 1972 that the Carruthers telescope was deployed. And Darlene's saying, "Oh, I can come give you an update at EclipseCon." Okay. And can you get the presentation slides? Let's see. I have stuff on my website. I've got a video of the slides actually. I just took this slideshow. I put some music to it, and it runs, I think, like 7 minutes long. So in the chat, I can drop you a link to that. And you went to the same high school as Charlie Duke. Oh, was he one of the astronauts on? No. Yeah, wait, but then I, I
Yeah,
used to
Spencer's
know.
nodding yes.
Oh, okay, okay. I was like, that sounds really familiar, and because I was like, I used to know all the names of all the astronauts in history, but now there's like too many of them, and my brain is old, so I've forgotten them. But that's really cool.
Yeah, Duke was on 16.
He was on 16. Okay. Was he one of the landing crew, or was he the command module?
He was a command module.
Command module. Okay. So he didn't get to step on the moon. I always thought that that was the worst job of the three astronauts on those Apollo missions. It's like you get to go there, but you don't get to go down. Oh man, what a bummer. But all right. Let
Wonderful.
me stop sharing so that I can see your faces. There it is.
What is the first question that you want to answer, Brian, with the data that and your
Oh,
findings?
I was gonna say I don't know what the questions are. Um,
But the answer is 42.
yeah, of course it always is. Um, the I mean, I think the one of the things that I like about this mission is that it doesn't have a whole bunch of questions, right? It's kind of really focused on what is the extent of the exosphere, what is its density profile, how does it change with time, right? And so maybe, the first question that we'll probably be able to answer is like, well, yeah, how big is it? Right? So that'll be, I think, that'll be a fun one, right? Because it's a pretty simple thing, and we should get that pretty quickly and get a sense of, oh yeah, this is how big it really is. It's still pretty big because we're still about what? We're still about 40 days away from reaching L1. And Laura this morning mentioned on one of our mission management calls that in the calibration images they've been taking, the exosphere is still bigger than the field of view. So
Wow.
big.
And so, like, does it count as being in the exosphere basically as long as you're encountering those hydrogen atoms you were talking about?
Yeah, and it becomes it's always one of these weird things where you like, where does the exosphere end and just interplanetary space begin? And that's it's sometimes pretty hard to define, right? Because there'll be some fraction of particles that are just barely gravitationally stuck to the planet, and then, the larger fraction are just slowly leaking away. This is like I've had this conversation. I won't call it an argument. I'll say like a conversation with people about like Mercury. Does Mercury have an atmosphere? And I argue no. I'm like, but it kind of has an exosphere. Like
Mhm.
there are particles that are leaking away from its surface and but they're on mostly ballistic trajectories, so it's mostly an exosphere. I wouldn't call that an atmosphere myself, but other planetary scientists might, and I'm not a planetary scientist, so I
Yeah,
should
I
probably
think
defer to them.
I think the team at Boulder with David Brain, Professor David Brain, they're publishing a paper, Mars as an exoplanet. Anyways, they're looking at I think they would say that the exosphere is part of the atmosphere from like an exoplanet perspective.
Okay.
But from a human perspective, I agree, it's so far away.
Well, and the density is so low, and we, in the space age, we tend to define, like I was saying before, we define space as beginning above the mesosphere. So even the thermosphere is kind of in space, right? But the thermosphere is gravitationally bound to the planet, so you want to spend a whole hour trying to get Dr. Lin to explain how they knew the diameter of the sun.
Because
Oh.
it's a gas. I was like, how do you know a diameter
Oh.
of a gas ball? And it took about an hour, but I finally got the answer from him, which is they decide on a definition by density and then they take an average. But it took a very long time to get him to answer that.
Yeah, yeah. Well, yeah, that actually is a pretty good question. Yeah, because, I think the photosphere is defined as, it's like a surface where the majority of visible photons are not being scattered by electrons. So, but even that's it's a shell. It's not a two-dimensional surface. It's like a shell of space where that occurs over. Let's see. Russell said we are still arguing about where the solar system ends. Yeah, yeah. In fact, I think with Lynn Kaminsky, I'm probably going to have this conversation because one of our notes about the astro curriculum I'm doing is I was in the activity that I do where we do a scale model of the universe. I stop at the heliosphere and call that the edge of the solar system. And the reason I do that is because it's physical and it's observed, and also it does. If we used the Oort cloud for the activity, it wouldn't work because the activity requires that when you zoom out to the size of the solar system, that what the sun would be visible on that scale. And so at the heliosphere, the sun is the size of a salt grain. But if you went to the Oort cloud, the sun becomes microscopic, and then that defeats the purpose of the activity. So that's the real reason why I make the solar system and the heliosphere, because I don't want a microscopic sun in my model.
Does anyone want a microscopic sun in their model? Well, I think on that note, everyone, we've reached time for this meeting. A huge thank you to Brian Mendez for coming and talking to us about Carruthers. I had no idea about Carruthers until just now. I too know Brian from other projects that we've worked together on, including this one and our neurodiversity network. So way cool to hear about what this spacecraft is going to do and how many eyes it's got and how much power it has and can is generated by the sun. Um, so I wish all of you a lovely evening. I will, how about when, Brian, you hear from or you get your first images from the spacecraft, I'll send it out to our listserv so everybody gets to see them.
Oh, sure. Yeah.
Cool. Well
Yeah.
then,
I'm sure we'll put them up at this link that I just put in the chat, and that's
oh
also
good.
where the video I mentioned of the slideshow is. So if you want
Awesome.
to grab that, feel free.
Cool.
Although, you know what? Well, I guess you could use it. It's on YouTube. If you actually want the MP4 file, I could probably share that with you. I have it on a Google Drive somewhere.
Oh, cool.
There's also a 3D model of the spacecraft on that page, and that's kind of fun to play with.
That's super
When I
cool.
get around to it, I'm going to see if I can turn that into a file that could be used for 3D printing, but I have to learn how to do that.
If you do
It's
it, I
more
want to print
complicated
one.
than I would have hoped, as it turns out.
I believe that.
Yeah.
All right. Thank you, everybody. Laura, any closing words before we say goodnight?
Nope, just thanks to Brian again. Another lovely talk. I loved it. I
Likewise.
learned some things as well. It's so fun to see it all happening.
And she's a heliophysicist, so that's a big deal.
And I know I know the project scientist very well, and I know in in 2012 he said, "I want a satellite out in space looking back at Earth, the exosphere." So it's pretty fun, but I didn't. I mean, I was like, okay. I did
Have
not
fun.
probe like Darlene did with Bob Lynn. I just said, that sounds cool. So it's pretty cool to actually see it being launched, and it'll be amazing to actually have that data from those words uttered to a scientific instrument and satellite. It's quite a journey. 2012 to 2026, 14 years. A lot happens in 14 years.
Your
Yeah,
kids
fair
get
enough.
really weird.
Yep.
Okay, I'm gonna officially stop the recording, and then I think, Brian, if you can just stay on and do the Google Share Drive for Kaz and Heather,
Oh,
that'd be
sure.
awesome.